Hello, everybody. So over the weekend, I graded the exam number 4, and thank you for submitting those. Um, and also, I published the grades on GradeScope, and I posted the answer key to the exam number 4. The average on the exam was I think it was a 79, which was just great. So let's just keep that up for the final, which is next week. Before the final happens, I'm going to post a study guide for the final, and I'm also going to post a practice final that you might like to take a look at. I haven't quite figured out what the logistics of the final are going to be. I'm thinking of doing something similar to exam 3 and exam 4, where I release the final at a certain time and to take into account people who have extra time and who are in different time zones and so on and so forth, give about the same time interval. So that's what I'm thinking of, trying something that looks similar to exam number 3 and exam number 4 as far as the logistics are concerned. So this today's lecture, I'm going to talk about proteins. But before I do that, I'm wondering, does anyone have any questions about anything? Any questions about anything before we get into today's lecture? Okay. So we've been talking. All right. Could you please post the recordings of last Wednesday? Oh, yes, I will. Thank you for reminding me. Anything else? Okay, so let's get on with today's lecture material. So we've been talking about amino acids, and the amino acids, as we've said many times, are the building blocks of proteins. And proteins have many structural and chemical uh, roles to play in the physiological system. So let's just look at some pretty pictures of what exactly proteins do. So for a lot of us who might be interested in food and food chemistry and biochemistry and metabolism, protein is what's for dinner, right? And so I see a lot of meat here, but also tofu if you're vegan or vegetarian, tofu, uh, eggs, so on and so forth. That has protein in it. But protein is so much more than something that you eat. Anyone out there like to cook? Maybe you know that brown food tastes good. Look at the steak, all of that caramelization on the surface there. And this looks like flan or something like that, all of that great caramelization. This is the product of the Maillard reaction. This is what happens when protein gets together with sugar. It's a chemical reaction called the Maillard reaction, and a lot of the very good tasting stuff is created in the course of that reaction. But protein is so much more than something for dinner. So let me show you some pictures of some of the structural roles that proteins play. Well, it's structural material. All your muscles are made out of protein. That is what is, most of the soft tissues of your body are made out of protein. Your hair, well, that's protein, right? So this lady has a very nice head of hair. Wonder if it's real. But hair is made out of protein as well. So that's protein as a structural material. Your nails, your Cartilage, that's also made out of a special kind of protein as well. Soft tissues, your heart, your lungs, your intestines, your stomach, all of your soft tissues are also made out of protein, where again, we see protein exercising its role as a structural material. Something that is very relevant now is another role of protein, and that is most of the bad effects of viral infection are a result of the virus getting into the cell and hijacking the cell's biochemical machinery to make viral proteins, so that the virus disables the production of human being proteins, and it takes over the cell to produce viral protein. The virus isn't eating protein. What the virus is doing is that the viral particle is encapsulated in a protective sheath called a capsid. And here we see three different viruses here. This is a bacteriophage. And so it is encapsulated in this protein coat. This is tobacco mosaic virus. This infects the tomato plant, and related viruses that attack other kinds of plants. It is encapsulated in a protein sheath. So this is HIV virus, and this kind of looks like, if you've seen pictures of the coronavirus, which I'll show you in a second, or something similar, you'll see all of these projections on the surface. Those are glycoproteins, where the protein has reacted with carbohydrate, but the protein is encapsulated in a protective sheath of protein. And this is why people die of viral diseases, because the virus gets in the cell, it begins producing viral proteins rather than human being proteins. The number of viral particles in the cell becomes very large, and eventually it ruptures the cell. And you know how we've said so many times, you're 85% water? Well, all of those cells get ruptured, and pretty soon, this is happening inside your lung with the COVID-19, your lungs fill up with water. Where did all that water come from? That's from ruptured cells, where the virus has hijacked biochemical machinery. It's making its own proteins. It's not making the proteins that you need to survive. The cell ruptures, your lungs fill up with water, you die of pneumonia. Okay, so this isn't COVID-19, but this is a related virus, SARS. And so I'm sure you've seen pictures like this in the media. And what you're looking at here is a cross section. The surface of the virus has these glycoproteins. This is chemical compounds that happen when sugar reacts with protein. And the various coronaviruses use these projections to latch on to the cell surface. And the viral particle as a whole is encapsulated in a protein membrane. Inside the cell, right, that protein membrane, that capsid, that is its armor against destruction of the viral particle. And inside the viral particle, it's RNA or DNA. It's RNA in the case of coronavirus, is wrapped around a protein as well called a histone. Now, the reason Mother Nature has used these protein coats to surround a virus, to protect a virus, is because a protein, as we'll see in a minute, is a polyamide. It is a polymer of amino acid polymer. And the amide functionality is very rugged, right? Remember, in the laboratory, if you want to tear down an amide, you have to use concentrated acid or concentrated base and boil the hell out of it for many, many hours. The amide functionality, and a protein is a amide polymer, is very tough. It's very resistive to degradation. And so that's why Mother Nature has selected these proteins to protect the viral particle. Okay, proteins are the polymers of amino acids. And so we talked a lot about amino acids last week. So these are just some pictures of the various amino acids, their molecular weights, the pKa's, and their abbreviations. Okay, and we see that the amino acids, there's the name of the amino acids. We know that they're associated with the pK of the carboxylic acid group, and also associated with the pK of the amino group, of the ammonium group, and some of them have side chains. Okay, so what I want to talk about, and then I'll return in a second to this slide up here. Where are you? Okay, so let me see if I can make this a little bit bigger. Okay, so the amino acid has a 3-letter abbreviation. That's the one I like to use. It's kind of old-fashioned, but if you see this 3-letter abbreviation, that is much more suggestive of what the amino acid really is, rather than the more modern 1-letter abbreviation. G stands for glycine, but glutamic acid also begins with G. What is its 1-letter abbreviation? And E. So that doesn't seem very satisfying, does it? Leucine begins with L. Its 1-letter abbreviation is L. But lysine also begins with L. And what is its 1-letter abbreviation? K. So you don't have to memorize any of these abbreviations. If you're lucky enough to take biochemistry, the professor there will no doubt make a big deal out of both the 3-letter and the 1-letter abbreviation. But I just want you to be aware that amino acids have these 2 systems of abbreviation. Okay. That's wrong. Speaker view. Okay. So proteins are important. So let's talk about proteins. What is exactly a protein? It's a polymer of amino acids. And the protein, so a bunch of amino acids get together, and the protein is written in a standard way. It's so-called, we have the N terminus, and then you have the C terminus. So an example of a simple polymer, very simple one, and I want to draw this at pH 0. We would have, there's our first amino acid. There's our first amino acid. The side chain here, that's the alpha carbon. The side chain here is a hydrogen. So that's the amino acid glycine. And now the amino acid is a polymer of amino acids, and the amino acids are linked together by amide bonds. But in a protein, the amide bond is called a peptide bond. So there's our first amino acid. Next amino acid would look like maybe something like this. So that's the side chain here of this alpha amino acid. That's telling me that's the amino acid alanine. Okay, and so now maybe we have another amino acid in this protein. The proteins are amino acids that are linked together by amide bonds. In a protein, they're called peptide bonds. So the next amino acid could be maybe something like this. And I'm going to put is phenylalanine. That's the side chain of the amino acid. And then let's see, let's wrap it up. Let's put another amino acid here, maybe something like this. And since I want to look at this at pH 0, okay. So there's our there's an example of an amino acid. This guy, that's the peptide bond. That's the peptide bond. So is this one. So is this one. So it is the protein is a polymer of amino acids, and it's hung together with these peptide bonds. The free nitrogen, the nitrogen atom that is not involved in a peptide bond, this is called the N-terminus. We see in this peptide here that all of the nitrogen atoms are involved in amide bond or peptide bond formation, except this one. So this is called the N-terminus. It's the nitrogen atom that is part of the protein chain that isn't involved in amide formation. And we see that all of the carbonyl carbons of the protein are involved in amide bond formation, or are involved in this peptide bond, except for this one, the quote-unquote last amino acid. This is called the C-terminus. So this is the standard way of writing a protein, from the N-terminus to the C-terminus. Okay, another way of writing this very same peptide, because these molecules can get gigantic, that's where the abbreviations come in. So this amino acid here, that was glycine. The next amino acid was alanine, right? I'm using the 3-letter abbreviation. This stroke here represents that peptide bond, right? It just take forever to draw all of the atoms and all the bonds in the protein. So this is just one of the abbreviations. The next amino acid here was phenylalanine. And then the last amino acid at the C-terminus was another glycine residue. So it would be written like that. Okay, so that's using the 3-letter abbreviation. There's also the 1-letter abbreviation. But when you see a peptide, when you see the protein written in this way, the implication is this is the N-terminus and this is the C-terminus. As I said, there's also 1-letter abbreviations. So let's take a little look at that for a second. All right. Okay, so if you look at, all right, so here's a big or a bigger protein, right? This is called beefy meaty protein. That's its nickname. And we see this is the free amino terminus over here. That's a lysine residue, then a glycine, then an aspartic acid, so on and so forth. So here are the 3 letters. Here's this protein written in that 3-letter way, but it's faster to use the 1-letter designation. I don't like it because I can't, I have to memorize which amino acid is which, but this lyse, gly, as, blue, ser, lu, ala, all of that can also be transcribed using the 1-letter abbreviation. K is lysine, G is glycine, D is aspartic acid, and so forth. And you can have some fun with these 1-letter abbreviations. A lot of you are in Sargent College. Well, you can string together amino acids using that 1-letter abbreviation, and you come up with SARGENT. So that's something this lady has done, or something similar that this lady has done. The love protein. See her tattoo here? Yeah, the love protein. Now, this is not a protein that if you ingest it or slip it into someone's drink on a date, they won't fall in love with you. That's not what it is. This is simply if you were to take amino acid L, which is leucine, amino acid abbreviated O, which is ornithine, B, which is valine, and E, which is glutamic acid, and string them together as a protein. There's the free amino terminus over here. There's amino acid L, amino acid O, amino acid B, amino acid E. There's the carbon terminus over here. And now she put little hearts on all of the carbonyl oxygens. I haven't gone through here to check the stereochemistry here, but I think that it might be right. Anyway, so you can have fun with these one-letter abbreviations. Just thought you might like to see that in case you're getting a tattoo. Proteins can be huge, right? This beefy, meaty protein, that's 1, 2, 3, 4, 5, 6, 7, 8 amino acids strung together. This is 4 amino acids, but amino acids can get together to make huge proteins. So this is HIV-1 reverse transcriptase. This is the enzyme that HIV uses to gain entry into the cell. And what we're looking at here is that just trying to get a handle on how big and complex some of these molecules can be. I'll have more to say about this later. This is maybe if you're a runner or a jogger, you know about endorphins and enkephalins. These are so-called natural painkillers. It's a small protein. There's a tyrosine residue there. There's a glycine residue, phenylalanine, and then this is methionine over here. So this is 4 amino acids that get together to make this endorphin, natural painkiller, supposedly runner, you know, this is like a marathoner. He's just run 26 whatever miles. He's in probably should be in excruciating pain, but he isn't because his body is flooded with this endorphin, this natural painkiller. So somehow he can resist, he can keep on keeping on. Anyone thinking of having a baby? Well, you're going to make a huge reliance on natural painkillers because let me tell you, I haven't experienced this myself, but I've heard that giving birth is quite painful, right? And so if you want to do it with natural childbirth, drug-free, then you're going to rely on these natural painkillers, which are these small proteins. My suggestion to you would be to go with the prescription stuff and get an epidural. All right. So let's practice drawing the structure of some proteins. Okay, so you always have access to that table of the amino acids and you know what their side chains are and all of that. But just to speed things along here, let me just show you that glycine, okay, and all of this is at pH 0. So that's glycine. This is aspartic acid, right? I'm drawing the structure of these amino acids at pH 0. Oh, and maybe phenylalanine. It's another simple one, put to right, that would be that. Okay, so this is at pH of 0. What if I were to ask you draw the peptide phosphate, glide. Draw that peptide at pH 7.4 at physiological pH. So let's try that. Remember, the protein is an amino acid polymer, and the amino acid, the protein is strung together as a polyamide. And just like when we were studying the synthetic polymers, there is a repeating unit in the protein, just like there's a repeating unit in the synthetic polymers. And the repeating unit, the pattern here, is going to be the nitrogen atom, the alpha carbon, and then the carbonyl carbon. Right? That's the repeating unit that we see in the polymer, in the protein. And of course, this alpha carbon can have any one of 20 different groups and of the proteins, the amino acids that are coded for by DNA. So that's the pattern that you see. Nitrogen, alpha carbon, carbonyl carbon. And then we start all over again. Nitrogen, alpha carbon, carbonyl carbon. Okay, so for aspartic acid, that would be this one. Nitrogen, alpha carbon, carbonyl carbon. Nitrogen, alpha carbon, carbonyl carbon. Nitrogen, alpha carbon, carbonyl carbon. So I have 3 amino acid residues in my protein. And so what I've done here is I've drawn the backbone of the protein. Now I'm going to finish it off by putting in the rest of these substituents and also at their proper state of protonation for pH 7.4. Okay, so our first amino acid is aspartic acid. That's this one at pH 7.4. We can look up the pKa of these protons on our table. We see they're about 9, so that at pH 7.4, these are protonated. Okay, the side chain of aspartic acid is this carboxymethyl group, and I look up the pKa of this proton here, and I see it's in the 2 somewhere, so that at pH 7.4, that is ionized. Okay, so that's what our aspartic acid will look like in this protein. Okay, now it's time to get in the next amino acid, which is glycine, which is this one. So this is an amide nitrogen. The pKa of this proton is way outside of the pH range, so it's just always going to be there. The alpha carbon of glycine is just 2 hydrogens, so we don't have to do anything special there. It's already done for us. Okay, now it's time for our next amino acid residue, which is phenylalanine. So this is a mid-nitrogen, has a proton on it. The alpha carbon of phenylalanine is this phenyl methyl group. And now we've come to the C terminus of the protein. And at pH 7.4, I look up the pKa of the carboxylic acid proton in phenylalanine. It's in the 2s, so that it's ionized at pH 7.4. So that's what this protein would look like at physiological pH. And we see it has an overall charge of -1. This would be the dominant form of this protein at pH 7.4. It has a -1 charge. And so it would probably be rather soluble, right? Because remember the isoelectric point, we talked about that last time. That's the pH at which the amino acid is least soluble, and the dominant form is usually going to be neutral. So this is negative. It's probably going to be pretty soluble in water solution. Okay, so this is how you draw an this is how you combine amino acids to draw a protein. You need to know the structures of the side chains of the amino acids. You need to be told what the pH is, and, and then you can decorate the backbone of the amino acid, which has all of this nitrogen atom, then the alpha carbon, then the carbonyl carbon. Nitrogen, then the alpha carbon, the carbonyl carbon, so on and so forth from N terminus to C terminus. This sequence of amino acids, ASP, GLY, PHE, this is called the primary structure of the protein. So this thing here, this is called primary structure. This is the sequence of amino acids. And like we said before, it is conventionally written from the N terminus to the C terminus. But proteins have a lot of other structural motifs besides primary structure, besides the sequence of amino acids. So let me show you some pictures about that. All right, so here's an important protein, insulin, right? This controls sugar metabolism. And we see that insulin is actually two chains, and what is illustrated here is the primary structure of insulin. It's the sequence of amino acids. Here is the N terminus of chain A. It's a glycine residue, then an isoleucine, valine, blah, 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 all the way down to the C terminus of the A chain. And here's the B chain of insulin. Again, it's written from its N terminus. First amino acid is phenylalanine, then valine, then asparagine, blah, 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 all the way down to the C terminus. So see that the protein can be very big. Here, I haven't bothered to count how many amino acids there are. Just looking at it, I'm thinking maybe 30, 40, something like that. This is primary structure, the sequence of amino acids, what the amino acids are going from the N terminus to the C terminus. But proteins have a lot of other structural motifs besides just the sequence of amino acids. Here we see the so-called secondary structure of the amino acid, where the amino acid has regions that are helical, like corkscrew. And so what we're looking at here in this picture is, where's the repeating unit? N alpha carbon, carbonyl carbon, and then it repeats, N alpha carbon, carbonyl carbon. So this is a protein. We spotted the repeating unit, R varies, but it arranges itself into this helix, this alpha helix, corkscrew. Then there are regions of the protein that adopt what is called the beta-pleated sheet, which is this corrugation. It just looks like a piece of paper that you got it folded over several times, and it's like this zigzag where one chain of the beta-pleated sheet, one segment of the chain is attracted to a second segment of the chain in an anti-parallel way with hydrogen bonds. Okay, so this is the secondary structure of the protein. You have regions that are helical, you have regions that adopt this beta-pleated sheet. So if you're lucky enough to take biochemistry, you'll see, I'm sure the professor there will make a big deal out of these so-called ribbon diagrams, which we've talked about several times. Maybe we're not exactly clear of what we were looking at. But what we see here is there's the alpha helix, right? This is the protein ubiquitin. This is the alpha helical region. There's an alpha helical region. There are a bunch of amino acids here. And these green arrows represent the regions of the pleated sheet. So it's always one arrow pointing in one direction and another arrow pointing in another direction from N terminus to C terminus. So this arrow is pointing this way, so this must be the C terminus over here. And so that's secondary structure. So see, there's primary structure of insulin. Here's the secondary structure of insulin, where we have some alpha helical regions, and chain A and chain B are held together by see these two arrows here? That's regions of the beta pleating. Okay, what else do I got here? All right, now in addition to primary structure and secondary structure, the protein also has tertiary structure. And this tertiary structure, this is how regions of the protein that are far away from each other in the sequence are linked together, most of the time to adopt a shape that is roughly globular. So this is the tertiary structure. And so we have hydrogen bonding, right? We see this in also an element of secondary structure. We see hydrophobic interactions where amino acid residues that don't dissolve in water very well are attracted to each other. We see ionic bonds, but probably the most important and the most interesting aspect of tertiary structure are these disulfide bridges. And so what is happening here is that on this, in the primary structure here, we had a cysteine. Remember, cysteine side group is CH2SH, and it got together, did a reaction with another cysteine residue, and this could be separated by dozens, hundreds, or even thousands of amino acid residues. But when these two hook up, it brings regions that are far away from each other close together. And so this is very, very important in biochemistry of a protein. Okay, so what's this? Okay, so this is trypsin. Maybe we're not ready to talk about that. I do want to talk a little bit about those disulfide bridges. A little bit more about these disulfide bridges. You see this like curl that has been introduced in this protein chain. If this weren't there, maybe it would be linear, right? We write the primary structure of a protein as if it were a straight line, but it isn't. We see that disulfide bridges bring together regions that are far away from each other. This cysteine and this cysteine got together to unite these two chains. And a loop is introduced into the protein. And we see this both on a macroscopic and on a microscopic level. Oh, you see this lady here? She has very curly hair. Why does she have curly hair? Because her proteins of her hair have a lot of disulfide bridges. And those disulfide bridges, they introduce loops and curls into the peptide, and that is manifested by all of these curls. If you have curly hair, you have a lot of disulfide bridges. If you have straight hair, you don't have that many disulfide bridges. Let me ask you a question. Don't raise your hand, just answer silently to yourself. Anyone here ever chemically straighten their hair? Okay, so this lady doesn't like the frizzies. She doesn't like the curls. So she's going to use this guy called Make It Straight. Wow, that's a very politically incorrect name for a product. And what this product has done is it has this thing thioglycolate, and this destroys the disulfide linkages. So suddenly you've gone from curly hair to straight hair temporarily because all of those disulfide bridges have been destroyed. Well, now this lady didn't have that great an experience with chemical hair relaxers because this stuff can be caustic, right? It can be very, very tough on skin, and so she suffered burns here. So what this chemical hair straightening that gets rid of the disulfide bridges and brings in that it straightens out the hair by destroying all of those loops. Okay, so we know that the protein has a lot of functional group diversity because the alpha carbon can have any one of 20 side chains on the alpha carbon, and we know that proteins not only have a primary structure but a secondary, tertiary, and there's even other levels of structure. All right, let's talk about making a peptide bond in the lab. Right, I'm not talking about how a cell creates a protein. I will at the last lecture, which is on Wednesday. Right now, I want to talk about how you would make a peptide bond, how you would try to make a protein in laboratory. Okay, so let's go to pH 0, a very acidic pH. And what I'm trying to do is I'm trying to get a molecule, let's say, I want to make that peptide, a glycine, and then an alanine residue. Okay, at pH 0, glycine looks like this. And at pH 0, alanine looks like this. And even if I put in acid and even if I heat it, what is going to happen? Nothing. No reaction. And that is because I want an acyl substitution. I want this OH to go away, and I want it to be replaced by the incoming nucleophile. I want this OH to break, and I want this this is supposed to be alanine, which has a methyl group here. I want this OH to go away, and I want this nitrogen to come in. But that's not going to happen at pH 0. And nothing at all is going to happen. Why? Because this thing is not nucleophile, right? I want an acyl substitution. There's my acyl derivative, and I need a nucleophile, but this doesn't, this nitrogen atom here has a positive charge on it. A nucleophile is something that's electron rich. How can something that's positively charged be a nucleophile? It can't. So I can't form that peptide bond at pH 0. So that's a leaving group. This could be a nucleophile, but if this guy comes in and attacks here, I'm going to get an anhydride, right? And that's going up the reactivity ladder from an carboxylic acid to an anhydride. That's not allowed. Nothing happens. Okay, so now let's try to change the pH so that this does become a nucleophile. So let's repeat this. So this was a dismal failure. I couldn't make a peptide at pH 0. Let's go to a pH greater than 9, in which now the nitrogen is going to be ionized. So I'm going to get NH2 there, O minus there. And so at pH greater than 9, the alanine residue will also, that proton on that nitrogen will also have gone away. Okay, now I'm at pH pH 9, so that means basic conditions. And if I try to heat it, what's going to happen now? Nothing. No reaction. That's a nucleophile, but now this nucleophile has to attack a carboxylate. And if you remember a reactivity order, this is at the bottom of the heap. And so I'm trying to make an amide from a carboxylate. I'm trying to go up the reactivity ladder. No good, right? So you can't make a peptide, you can't make a protein just by mixing together a bunch, in a lab anyway, just by mixing together a bunch of amino acids, absolutely nothing will happen. Okay, so that was a dismal failure. So now let's try something else. Okay, let's look at a partial workaround. How can we outsmart the amino acid to create a peptide bond in a laboratory, right? Just mixing a bunch of amino acids will not work. So now what I'm going to do is I'm going to take glycine. I'm going to take glycine. I'm going to be at pH of 0, low pH. I'm going to take glycine. And what I'm going to do is esterify the glycine, right? There's a carbonyl-carbon bond to something that's not carbon, not hydrogen. This bond is going to break. This is going to go away. Its place is going to be taken by the nucleophile minus a proton, right? So this is just acyl substitution, acidic conditions. So I'm going to use methanol just as an example. I could use any kind of alcohol, really. And so I'm going from, this expels water. So this is just a straight up acyl substitution. I'm going from a carboxylic acid to an ester, and the carboxylic acids and the esters are about the same level of reactivity, so this is okay. All right, and now what I want to do is, now I want to bring in the alanine, right? And so I want another acyl substitution where the alanine is going to attack here, kick off this this leaving group, but this is only going to be possible at basic pH, right? Because the incoming alanine can't be NH3+, it has to be NH2. So now what I have to do is adjust the pH, go to pH greater than 9, go to pH greater than 9, and so that is going to remove that proton from the NH3+. And now I'm going to add to this ester, I'm going to add my alanine, which will be in the same state of protonation, looking like this, right? And so now what I see is there's a carbonyl-carbon bond to something that's not carbon, not hydrogen. This is going to break off. That's going to go away. The nucleophile will take its place. I'm going from an ester to an amide. That's downhill, down the reactivity ladder. That is going to work. And so this removes CH3O minus. We're under basic conditions. And voila, I've made my peptide. I've made my peptide bond, right? This is the peptide bond that I was looking for. But this is just a partial. So we think that we've outsmarted Mother Nature, but not really, because this has its own problems. This guy doesn't know he's supposed to wait around this glycine doesn't know it's supposed to wait around for a molecule of alanine, right? So two of these guys could get together. This carbonyl carbon is just looking for an NH2 to react with. And so one of these molecules could get together with one of its own kind, right? It doesn't know it's supposed to wait for you to add this. Two of these molecules could get together and they could undergo this self-reaction. And the result here would be the result here is that we've made, this went in here, that kicked this out. We've made something we didn't want, right? We wanted to stick a glycine together with an alanine. Here, a glycine and a messed up esterified glycine has gotten together. And that's not the end of the story, because I see 1, 2, 3, 4, 5, 6. I could get it now an intramolecular acyl substitution. So this could do an intramolecular acyl substitution, and I could get something NC, NAC. That could form this, where this came in here, kicked out that leaving group. Whoa, I didn't want that either. So this is just a partial workaround to solving this problem. How in a lab do I stick together two amino acids to come up with a peptide bond, and can I synthesize big complicated proteins in the laboratory? So we'll get some of this, but we'll also get this. And this guy is in a very rapid way, is going to cyclize to this with expulsion of methanol, by the way, over under basic conditions. Yeah. So there's a problem with making a peptide bond in a laboratory. We can't just mix together amino acids. We have to use some cunning, and even this level of cunning doesn't work out. At the Wednesday's lecture, we'll show how we can improve on this scheme, and then we'll talk more about primary structure. So that's all I have for you today. I'll see you Wednesday for the last lecture. Any questions about anything? If not, I'm going to sign off. Okay, see you next time.